converge to Q. This might be a good place for another picture. To say the limit of f of x is not Q, let's see. Let's come back to this picture where it was obvious. Suppose this is Q, and this is P. To say that the limit of these, this is, as x goes to P, this limit's not Q, means that there is an epsilon around Q, maybe, there's just a picture here. Can you see an epsilon around Q which would work? Yeah, pretty easy to see. How about this one? Certainly that's going to have problems. You're going to have problems landing within this epsilon ball around Q. In fact, even if Q were at the end, you'd still have a problem, right? Let's make this even more interesting by putting Q here. Maybe Q's likely is this one. Well, take this epsilon ball. You're in trouble on the left, aren't you? Such that for every delta bigger than 0, I don't care what delta you give me, there's a point. So no matter what delta you give me, here's a delta ball. I don't care what delta ball you give me. Maybe this one. This is huge. Or very small. It doesn't matter. I could take a smaller one. There is a point in this delta ball which is close to P, but whose image isn't epsilon close to Q. Do you see one? Yeah, one on the left here. There's a point, little x. Image is not within epsilon. Okay? Happy with that? Jing-Jing's happy with that. Jeremiah's saying, okay, well, good. So let's use this to find a sequence. What sequence would you suggest constructing that would approach P, but whose image does not approach Q? Deltas? Good. Smaller and smaller deltas. That's nice. Here we go. So we'll find a bad sequence. We propose a bad sequence. This one's bad. Here we go. Let's use delta n equal 1 over n. There's smaller and smaller. And choose x sub n by this condition, which I will call triple smiley. Would you agree that tells me there's a delta that for that epsilon, that there's a delta that I can choose an xn. And if I let these deltas get smaller and smaller, then what we see is xn clearly converges to P, yes? But then what else is true? All their images are what? Yeah, but the distance of f of xn is bigger than epsilon by smiley. So f of xn does not converge to Q. End of story. They are the same thing. So it doesn't matter whether you want to talk about sequence criterion or the sequence definition, characterization, or the epsilon delta characterization. They're the same thing. Okay. But one thing that's nice about the sequence characterization is we've already proved lots of theorems about sequences. And they all carry over now to limits of functions. So, for instance, what do you know about sequences? Well, limits of sequences are unique, aren't they? So limits of functions are going to be as well. So from the theorems on sequences, here's what we know. Limits are unique. You can't have the limit of a function be p and p prime, or q and q prime, unless q equals q prime. What else? Sums of limits equals limits of sums. Products of limits equals limits of products. They all follow because you have a sequence characterization, and those particular sums and products are going to converge as well to the things you think they should, right? So limits of sums are sums of limits, etc. You can say the same thing for products. Right? What do I mean by that? What I mean is you want the limit of f of x plus g of x. Guess what? It's the same as the limit of f of x plus the limit of g of x. These are all x going to some p. I'm not going to write all these out, but the point is all those theorems carry over. That's the beauty. Okay. Okay. Those are functions for, I guess these are functions for into where y is r. I guess these don't make sense otherwise. Okay. Actually, if y is a greater Euclidean space, well, you have some kinds of products, right? Dot products. You could prove similar theorems as well. Okay, great. So what do we have? We have described what it means for a function to have a limit. Now, one of the places where this is going to be very important is to describe what it means for a function to be continuous. So we're going to take a couple-minute break, and after the break, we will define continuity of functions. Okay? Let's take a couple-minute break.